Hi and welcome to Volumetrics. So we are going to solve some problems now, and on the go we'll also discuss some theory relating pertaining to these very simple problems. So let us start with the first question now. A short hollow circular cast iron supports an actual compressive load of uh, 50 kilonewton. The ultimate stress in compression for the material is around 280 newton per millimeter square. It is decided to design the cylinder with a wall thickness of 5 mm and factor of safety of 3 with respect to the ultimate strength. Alright, so compute the uh, thickness required, minimum required outside diameter of the cylinder. Okay, so just to visualize this, I'll be drawing a schematic. So I have a column something like this. Uh, so inner and the outer diameter here, and this is what we know as the D, uh, and the thickness here that has been given is 5 mm, and it goes all the way below. Okay, so this is a column that we are going to have. Right, so this is under compression. All right, so with given all of this input, so we are going to have uh, the ultimate strength and the factor of safety. Right, so before we get into solving the problem, let us just discuss some theory concepts regarding this. uh, okay, now first of all, what exactly is sigma allowable? Right, so what is allowable stress? So allowable stress is nothing but of sigma yield or yield stress divided by factor of safety. Right, so this is for ductile materials. So, and sigma allowable would be equal to sigma ultimate divided by factor of safety for brittle materials. Right, so because in brittle materials we'll not be exactly knowing the yield stress, so we are going to take up ultimate stress in case of brittle materials, and we are going to divide that by factor of safety. Right, so what exactly is factor of safety? Factor of safety is again failure stress divided by working stress. Okay, so with this information, let me go back to solve the problem. Okay, now, so we know sigma ultimate, sigma ultimate, so that, and we also know sigma allowable. So we have to calculate sigma allowable, that is nothing but sigma ultimate divided by factor of safety, because this is a cast iron cylinder. Cast iron is a brittle material, so we are going to have to use the ultimate stress. So ultimate stress is what they have given us, 280 Newton per mm square divided by factor of safety is 3. So this gives me the answer of around 93.33 Newton per mm square. Okay, so now sigma allowable. So what does that give? Sigma allowable is given by the total compressive stress divided by the cross-sectional area, right? So I'll calculate the cross-sectional area now. I'll substitute this. 93.33 is equal to the compressive stress is 50 Newton meter, so that is 50 into 10 to the power of 3 divided by the cross-sectional area. So after simplifying this, the cross-sectional area would be equal to 535.73 mm square. Right, so now I'll have to calculate what is this cross-sectional area. I'll just go down and I'll solve here. Cross-sectional area, that is equal to the outer diameter area, so pi by 4 into d square minus pi by 4 into the diameter of the inner circle. Inner circle diameter is d minus 2t, right, whole square. So t is nothing but thickness of the column. Right, so here if I simplify this, I'm going to get pi by 4. I'll take it as common. I'm going to have d square minus, I'll simplify this, minus d square minus 4t square and plus 4dt. So here d square would be cancelled, and in this remaining part I'm going to take out pi by 4 and I'll take t outside. So here I'm going to remain with so I'll also take 4 outside, so 4 and 4 would be cancelled. So the remaining part is d minus t. Okay, so now I'll substitute the a value, that is 535.73 is equal to pi into t is nothing but 5 mm into d is what we have to find out, minus t is again 5 mm. So now if we simplify this, the answer that we are going to get is d would be equal to 39.10 mm. Okay, so let's move on to the next question. Okay, so next question. So we are going to have a structural steel has a shearing ultimate strength of 310 megapascal. So the ultimate stress is given as 310 into 10 to the power of 6 pascals. So determine the force P necessary to punch a 25 mm hole. So D would be is given as 25 mm hole through 10 mm thickness. So thickness is 10 mm. So I'll just draw a schematic just for our understanding. So this is how the punch hole part would look like. So we are going to have a compressive force here, that would be P, and for that a stress would be developed in the opposite direction in the surface or the shearing area. Right, so here it is given as 10, the thickness is given as 10, and the diameter is given as 25 mm. Okay, so with this knowledge, again we are going to apply the same thing to determine the maximum P or the P required. So the given is, so sorry, this is not sigma, this would be tau ultimate because we are shearing, right? So yeah, first of all let's apply the formula for shear stress. That would be the compressive force or the shearing force divided by the area. So here the shearing force is P. I don't know what is P. So if I substitute if I equate for P would be equal to tau ultimate into pi into d into t, right? So circumference of this inner circle and the height of this particular cylinder. Right, so this would be the shearing area into the ultimate stress. So we are going to let me substitute all the things. Ultimate stress is 310 into 10 to the power of 6 into pi into diameter is 25. So here this is in Newton per meter square. So this is mm. I'll convert that to uh, meter into 10 to the power of minus 3 into 10 into 10 to the power of minus 3. So 10 to the power of minus 3 into 10 to the power of minus 3 into 10 to the power of 6 would be cancelled out. So the remaining is, if I simplify, I'm going to get 243.47 kilonewton as the answer. Okay, so moving on to the next question. Okay, a metal sphere of volume 7500 mm square. So volume is given as 7500 mm square, sorry, mm cube, is subjected to all fluid pressure of 200 megapascal. So sigma x is equal to sigma y is equal to sigma z is equal to 200 into 10 to the power of 6 pascal. Okay, the bulk modulus of the material is 1 into 10 to the power of 5 Newton per mm square. So bulk modulus is represented by the letter K. K is equal to 10 to the power of 5 Newton per mm square. So since it is in Newton per mm square, I'll convert this into the Newton per mm square. So I'll have it as 200 Newton per mm square, just to avoid all the confusions later on. So they've asked us to find out delta V. So here, let me just write down the formula for K. K is nothing but sigma divided by epsilon v. So stress divided by volumetric strain. So volumetric strain is again given by delta v divided by the original volume. So here let me just calculate epsilon v here, the volumetric strain. So that is given by sigma. All the direction sigma is same, so I'm going to take it as 200 divided by k is 10 to the power of 5. So here epsilon would be equal to 0.002, and again epsilon v is equal to delta v by v, applying this formula. So I'll have to calculate delta v. I don't know this. The original volume is 7500. So simplifying this, I'm going to get delta v would be equal to 0.002 into 7500. So that would be equal to 15 mm cube. Right, so here the answer is 15 mm cube. Okay, moving on to the next question. Okay, a circular bar of dia 50 mm, so diameter is given as 50 mm, is subjected to a pull of 50 into 10 to the power of 3 Newton. The elongation in the length was recorded as delta L is given as 0.09 mm, and the reduction in diameter is, so there is a typo here, so this would be 0.006 mm. Okay, so delta D, the change in the diameter, is 0.006 mm. The Poisson's ratio and the value, so calculate the Poisson's ratio. So I'll have to calculate mu, I'll have to calculate the three moduli, that is E, K and G. Take the length of the specimen as 250 mm. Okay, so while solving this problem, we'll talk about the three formulas or the relationships which connect all the three constants. So let me just start with, let me just first calculate the area of cross section here. So the area of cross section A would be given as pi by 4 into d square, that is 50 square, so which is nothing but 1963.49 mm square. Okay, so I'll calculate the elastic modulus, so that is nothing but E. So to calculate E, I'm going to have E is equal to sigma by epsilon, so longitudinal stress by longitudinal strain, so that is nothing but stress is given as P by A, P divided by A into epsilon. So that would be equal to, P is given as 50 kilonewton, 50 into 10 to the power of 3 divided by cross sectional area is 1963.49 into epsilon is change in longitudinal, change in length divided by original length. Change in length is 0.09 divided by original length is 250. Right, so if I simplify this, the elastic modulus would be given as, would be something like this: 7.07 into 10 to the power of 4 Newton per mm square. Okay, let me now calculate the elastic Poisson's ratio. For the Poisson's ratio, formula is given by lateral strain divided by the longitudinal strain. So lateral strain is given by delta D divided by D whole divided by delta L by L. So now this is nothing but 0.006 divided by the original diameter is 50 mm divided by 50 whole divided by 0.09 divided by the original length is 250, and if I simplify this, I'm going to have 0.33 as the Poisson's ratio. Now the bulk modulus K, now it is given as, now there is a formula to which relates elastic modulus and the bulk modulus, so which is given as E is equal to 3K into 1 minus 2 nu. Right, so in this I know the elastic modulus, I know the nu value, only K is unknown. So if I substitute all of them, I'm going to have 7.07 into 10 to the power of 4 is equal to 3K into 1 minus 2 into 0.09 33. Okay, so now if I simplify this, K would be equal to 6.93 into 10 to the power of 4 mm square. Okay, so the next is the rigidity modulus or the shear modulus G. So now again there is a relation which equates the elastic modulus and the shear modulus, which is given as E is equal to 2G into 1 plus mu. Right, so now if I substitute again, E is 7.07 into 10 to the power of 4 into 2G, I don't know the value of G, plus 1 plus 0.33. And now if I simplify this, G would be equal to 2.66 into 10 to the power of 4 Newton per mm square. Okay, and also there is one more formula which relates all the three constants, so which is given as E is equal to 9k into G divided by 3k plus G, right? So these are the three formulas which we rigorously use while solving the problems in these type of problems. Okay, so let's move on to the next question. So the last question of this video. So okay, a high strength steel rod is equal to 200 GPa. So E is equal to 200 into 10 to the power of 9 pascals. Or so let me check the other dimensions here. So we have mm, so I'll keep this in mm as well. So this is nothing but 200 into 10 to the power of 3 Newton per mm square. Okay, and sorry, mu. So here mu is what we have as the Poisson's ratio. Mu, I'll, for the sake of simplicity, I'll be using nu only. Nu is equal to 0.3 again. Is compressed by an axial force P. When there is no actual load, the diameter of the load is, so the original diameter is given as 50 mm. Okay, so in order to maintain the clearance, the diameter of the rod must not exceed 50.02. So I'll have it as d limit, so which would be equal to 50.02 mm. Okay, so what is the largest permissible load P? So they have asked us to calculate the maximum load. Okay, so here let me just calculate the lateral strain using this value. So for that I'll have to calculate the delta D value. Delta D would be equal to 50.02 minus 50, so that would be equal to 0.02 mm. So this is the change in diameter. So change in diameter divided by the original diameter is what we have as lateral strain. Delta D divided by D, so which is nothing but 0.02 divided by the original diameter is 50. So we have as 4 into 10 to the power of minus 4. Now again, longitudinal strain is given by stress divided by elastic modulus. So the stress that we have here is, we don't know the stress, so I'll be having P by A, so P, so which is maximum because I've taken as the maximum diameter here, allowable diameter. Now P max divided by the cross sectional area, which is nothing but pi by 4 into 50 square into the E that is given as 200 into 10 to the power of 5 Newton per mm square. Now if I simplify this, I'm going to have 2.54 into 10 to the power of minus 9 into P max. Okay, so I'll make use of the formula of Poisson's ratio. Again, nu is given by epsilon lateral strain divided by the longitudinal strain, so which is nothing but a new value is given as 0.3, that would be equal to 4 into 10 to the power of minus 4, which is the lateral strain, divided by the longitudinal strain is 2.54 into 10 to the power of minus 9 into P max. So in this equation the only unknown is P max. So if I simplify this, P max would be equal to 5.25 into 10 to the power of 5, so which is nothing but 525 kilonewton. So this would be the maximum compressive load that this can take. Okay, thank you for watching. Please stay tuned for the upcoming videos. Like, share and subscribe. Bye bye and see you in the next video.